All right, so let's get formally started with the slides in this class. I think the previous class we might have started a little bit of this, but I want to go over this all over again. And this time I'm going to use my iPad so that I can scribble freely on the screen, so that it's much more spontaneous and better than using the mouse to draw things on the screen. All right, so welcome to the course again. So in the last class, or in the first class, whenever it was, when I asked what's an OS, and some of you said it's a thing that sits between the user and the hardware, and that's totally true. So it's basically an intermediary between the user and the hardware, right? And yeah, and there are a few goals that the operating system needs to attain in order to be a good operating system, right? Something that people would want to use. So it depends on who is looking at the operating system, right? If the user is looking at the operating system, then they care about ease of use and performance. Okay, so they care about how easy it is for you to use the operating system, right? To use the computer, right? So if you click the start button, then they expect to see the start menu. Well, if that's not happening, then it's not easy for them to use the computer, right? If they want to start a program, the program should start as expected. If the OS is not doing that properly, then it's not easy to use. They are not getting what they're expecting to see, and then they would not like to use the computer. They'd rather just say, I will use something else to it. They also care about performance, right? For example, we guys use Excel a lot, so do you guys, right? And if there are a couple of columns and you want to apply a formula to create a third column, and if that's not happening fast enough, if the operating system is not able to assign enough resources for your process, that is Excel at this point of time, then no one would like to use the computer, right? So whenever the computer is not easy to use, or the computer is not performant enough so that the user is not finding it as a smooth experience, then the operating system is unable to attain its goals as far as the user is concerned. At the same time, the user is not concerned about resource utilization. Okay, the user is not concerned about resource utilization. They do not care how much CPU, how much RAM, or whatever have you given to them. All they care about is that the system is easy to use, and proper resource, and proper performance is being achieved. But at the same time, you may not be the only user on the system. Okay, so for example, on a laptop, you might be the only user, but if it's a server on which many people could be remotely logged in, right? And then you are not just the only user, right? So there might be, let's just say, 3 more users on the system, including you. There are 4 users. Just like you, they might have fired up a shell script, maybe Microsoft Word or whatnot, or they might be browsing the internet, and all of them need to find the computer easy to use and performant. So from the resource utilization point of view, the OS should be able to allocate hardware resources like CPU, RAM, and input-output devices fairly and efficiently to all the users and all the processes that those users have started. So the processes have to be allocated fairly and in an efficient manner. Okay, fairly as in, so if there are 2 users and you have 8 GB of RAM, and the entirety of the RAM is going to be occupied by the 2 users, then we would expect 4 GB each to be given to those users, provided they have similar number of processes, similar kinds of processes started at the same time. At the same time, if there is 2 GB of useless data present in the RAM, then that should be garbage collected by the OS. Okay, it should get into the dumpster, right, as soon as possible, so that it can be allocated to the users. So it should be done in an efficient manner, and it should be done in a fair manner. So the user cares about ease of use and performance, and at the same time, from the resource utilization point of view, resources have to be granted to these users and the processes that they have started in a fair and efficient manner. Okay, so let's look at the computer system structure. Okay, so how is the computer system laid out? So at the very bottom, you always have the hardware. Okay, and hardware can be things like CPU, your processor, your memory, input output devices like disk, printers, your displays, and so on and so forth. Okay, so out of these, a few of them, like the input output devices, they need device drivers to work. They need device drivers to work. But there are a few things like the CPU and memory, they do not need device drivers to work. They can work as such because they start working when the system boots up. And I will tell you in details what happens when the system boots up. Okay, so here is your OS. So the OS might use device drivers to handle things like input output devices, but for things like your CPU and RAM, it does not need device drivers, right? So on top of the OS, you have a setup system calls, right? So system calls are the interface that programs use to be able to get services from the operating system. And then on top of that, we have users. So users use programs. Programs make system calls to get whatever they need from the OS, and the system calls are processed by the OS with the help of device drivers and other mechanisms, as we will see throughout the course. All right, so I might have given this example, but let me do this all over again. So many of you might have heard about APIs, right? Representational state transfer, REST APIs. So these REST APIs sometimes they tend to give you CRUD operations, basically create, read, update, delete operations on certain database schemas, right? So these APIs are usually backed by business logic, and there is a DB sitting somewhere, and this DB might have schemas like there is a user database table, there is a there is an authentication table maybe, and there is a department table, and so on and so forth, right? And there might be some private schemas also, which are just internal to your tool. So if there is a client sitting here, then this client should not be able to access any of the schemas directly. This access should not be allowed. The client should only interact with the REST APIs. So this is where you get controlled access. Because the REST APIs tell you what you can see and what you can do on the system. Nothing more, nothing less. And then the REST APIs talk with the business logic. The business logic then talks with the database, and then they send the results back to the client, right? So the client does not have absolute power to read and mutate or change things in the database. They cannot do that. Similarly, users over here, they do not have direct access to hardware. They do not. They use programs, and programs in turn make system calls. And system calls are one of the only ways in which a program can get services from the operating system. For example, if there is a file on the disk, let's just say a users.txt in the root directory, and there are the names of a few users in there, and you want to add your name to that. So you cannot directly go get the hard drive and then locate the file and then manually change it. Well, why is that not allowed, you might ask? It's because it is not just your files that exist on the hard drive. Files of the operating system, files of many other users, lots of different things exist on the hard drive, right? So if we give access to all the contents of the hard drive, then how can we trust that your program will only edit your file and not corrupt the rest of the things on the hard drive? There is no guarantee. So basically, well, we might trust your program, but what if your program is a virus, right? So the operating system will not let access to the disks directly in the raw format, right? You have to go through system calls, and you have system calls like open, which can help you open a file, and then that will give you a file descriptor, which is a number which you can use in the rest of the code to identify the file. And then you can have system calls, right? Like read, write, and then once you're done, you can close the file. So all of these are system calls. And so once you open a file, let's just say you are not allowed to open the file in the write mode. So if you say open the file users.txt in the write mode, then the OS may not grant you access. It will say, no, you're not allowed to write to the file. You can only read that file, right? So this is how the operating system can enforce restrictions on access with the help of system calls, right? Is this idea kind of making sense to all of you?
Yes, sir.
Okay. All right, the same kind of thing that I was talking to you about, and we have also talked about this, right? Ease of use, good performance is what the user cares about. The user cares about these two things, right? But a computer can be shared by multiple users, right? And then if the computer is shared by multiple users, then we also need to make sure that the resources are granted fairly and efficiently to all those users. Okay, so how do you define an operating system? Well, there is no clear-cut definition of an operating system. You can call an operating system a resource allocator, right? It allocates resources in a fair and efficient manner. It's also a control program. And if your program is doing something funny, right? For example, if it is dividing by 0, so if you do 5 by 0, this is going to cause an exception. Or if you have an array which has 5 entries from 0, 1, 2, 3, 4 indices, if you try to access indices beyond that, right, these ones, at some point you will get a segmentation fault, because the OS now tells that, hey, your process has this much memory and the array is going to take this much memory. Well, that is what you have asked for. You are going beyond how much you have requested for the array, and you're going beyond that. Maybe fine, but the moment you step outside how much has been given to your process itself, that is when the OS is going to say, no, here you committed a segmentation fault, you are going to be halted. So, well, that is again one of the major ways in which the OS prevents bad things from happening to the computer. It should not crash the entire system, because multiple users might be logged into the system at any one point of time. So a bad program that you have written or you are trying to execute should not sabotage the efforts of other people to do their work. So what happens when a computer starts up, right? So how many of you have used desktops in your life? I mean, all of you have probably used laptops. So this question should not have been asked to you had you been like 10 years older, right? But since you belong to a generation where people don't even see laptops because they use tablets and phones. So how many of you have used desktops? Have people used desktops? Anyone? Raise of hands, please. Cool. So in a desktop, when you press the power button, then what happens? So you do not see anything on the screen for a while. You know why that happens? Well, let's visit that. So you have got a CPU, and the CPU will execute code. The code can come from RAM, okay? And when you start the computer, the RAM is basically empty. So what will the CPU run? Well, the CPU will run code in something called as a firmware. Okay, it's a firmware. It's a small IC present on the motherboards of computers on which code called as BIOS. BIOS is basically basic input output system. Okay, so this code is present on something called as firmware. Firmware is not called as hardware or software because it is something in between. It is not easy to change the contents of firmware because you cannot do it just like you format a pen drive. You need specialized hardware and specialized software to be able to change that. But It is not hardware because you can still change it. So when you power off your computer, you lose the contents of RAM. Okay, your contents of RAM, they are gone, but the contents of firmware will not be gone. They will always stay. So the firmware contains something called as the BIOS, and the CPU can also read contents of the firmware when it boots up. So the CPU will run the BIOS. The code for BIOS is going to be run by the CPU. So what does the BIOS do? So the BIOS does something called as post when the computer starts. This basically is called as power on self-test. It is going to test things like CPU, memory, keyboards, disks, etc. It also contains your graphics adapter. All of these things are going to be checked by the post process to see if they are working. If the graphics adapter is working and the RAM is kind of working, good enough to show something on the display, then at least you will start seeing the logo on the monitor. If the post process is not able to detect, or it detects a faulty graphics adapter, then it starts to beep. I think many of you might have heard that long and short beep sequence. And if you look it up on the internet and say that my motherboard is an Asus or an Acer or whatever motherboard, Gigabyte or whatever, and then this is the pattern that I'm hearing, what does this mean? And then they might tell you that, oh, maybe your memory is faulty, or maybe your CPU is not working, or your graphics adapter is not seated properly. Then you remove a few components of your motherboard and put them back again for it to potentially work again. At some point, you should make sure something is shown on the screen. Then, if your disks or your keyboard is not working, it will say no keyboard detected, or, could not find a bootable hard drive, right? Things like that. So the post process goes on fine. If everything is in working order, then the BIOS will then select the configured disk, whatever disk is configured, for the OS to load from. It is going to read sector 0 of that disk. Okay, so sector 0 of that disk is going to be read in order to get a bootloader. Okay, one example of a bootloader is Grub, the Grand Unified Bootloader. You basically get Grub when you install Linux on your computer. There are multiple other bootloaders also. So the BIOS is basic input-output system. This won't be able to load all kinds of OSs into RAM. So ultimately, we want the OS to be loaded into the RAM, right? So that the CPU is able to go further from there, right? So the bootloader is going to be loaded by the BIOS, okay? And then the bootloader then knows in specifics, right, how to load each of those different OSs. For example, Grub knows really well how to load Windows or how to load Linux, right? Especially the Linux kernels, right? So Grub is then going to look at further sectors on the disk and figure out what is the boot partition. From the boot partition, it is going to figure out where is the kernel, okay, the Linux kernel, and then it is going to take the Linux kernel and load it into RAM. And then it is going to instruct the CPU, start executing the Linux kernel. And when it starts doing that, at that point of time, the BIOS and the bootloader have no importance in the system. It is the kernel that is going to then set up the rest of the things. For example, it is going to properly set up the graphics adapter for it to be able to render 3D models, for example. Until this point of time, the BIOS was, barely able to show a few things on the screen. For example, you cannot use the BIOS to play games on your 3D card, your NVIDIA or ATI cards. It is the Linux kernel which is going to load the necessary drivers so that these things start working properly. Then it is the Linux, it's the kernel, right? Whether it's a Windows, Linux, whatever kernel, that is what is going to set up your network interface cards so that they get the IP address that's necessary for them to communicate over the LAN, right? And they will set up many other things, and then they will show you the prompt, like the username password prompt. At that point, users can log in and start running the user programs. So this is basically the overview of the process that is involved when a computer starts up. So if someone asks you in interviews that what happens when a computer starts up, and this is what you tell them. When you push the power button, the computer knows nothing what to run, so it refers to the firmware where the BIOS is stored, and the BIOS then does something called as the power on self test. It checks these things: CPU, RAM, keyboards, disks, graphic adapters. Whether it beeps to tell you if something is wrong, or if it can show something on the screen, then it tells you that these things are wrong, fix it. After everything is working fine, then it will figure out where to load the operating system from. For example, most of you probably know, if you press the F8 key or some other key as specified by your motherboard vendor, then it might also show you a list of disks. You can choose and say, okay, don't load the OS from the hard drive this time, but use the live distribution of Ubuntu from this pen drive and get me there. The BIOS can help you do that also. And then the BIOS then figures out the bootloader from the selected disk. The bootloader then loads the kernel into memory, and then your operating system then starts initializing the rest of the things in greater amounts of detail, and then shows you either a GUI prompt or a command line prompt where you can punch in your username and password and get started, right? Okay, does that make sense to everybody until now? Do you have any questions for me?
Please define what is sector 0 again.
Sorry, please, can you be a little bit louder?
Can you please explain what was sector 0 part?
Oh, the sector 0 part, right? Yeah. So disks usually have sectors, right? So if you look at a rotational disk, for example, a hard drive here. So there is kind of a spindle, right, on which different platters are there, and your read-write heads kind of move back and forth on top of it, right? So sector 0 is basically, a sector at the periphery. It is the first sector. So the disk is divided into cylinders, okay, which you will see in the last chapter. So there are no lines on the disk though, but you can think of this one thing as one cylinder. It is one set of adjacent concentric circles. It's basically a cylinder, and these cylinders are then divided into different sectors, right? It's like when you take a circle like this and you take another circle like this, you get a cylinder, right? And then if I just draw lines from the center, okay, so you see this is one sector. So there is a special sector on the disk. The first sector on the disk is called as sector 0. It is that sector which basically has the bootloader on it. And the BIOS knows that, right? And the BIOS will try to go to sector 0 and get the bootloader from there. And from that point onwards, the bootloader will then know better where the kernel is stored. Then the BIOS is not responsible for any of that. The BIOS is very basic, so it will do something very primitive like locate sector 0, get the bootloader, and then it is done. Does that make little sense to you? More sense to you?
Yes.
Okay.
Yes.
We'll learn more about this, when we go to disks towards the end of this course. Okay. How many of you have seen motherboards? A motherboard. Has anyone bought a motherboard, or has anyone tried to kind of repair their own computer?
Yes, sir.
Yes, sir.
Okay.
Yes,
so,
sir.
Okay. So you probably will remember that a motherboard kind of looks like a city, right? It looks as if, there are a bunch of roads on it and there are buildings on it, right? It kind of looks like that. So you will see lots of lines like this. And those lines, will just kind of, they tend to bend, and then, so these lines are basically called as buses. So this is basically a bus. A bus connects components on a computer. So the CPU is always connected to memory. Okay. The memory is also connected to different things. So this is basically a bus, a big bus on which things are connected to each other. Right? So this bus connects the memory to CPU. It also connects the CPU to the rest of the controllers. It also connects the controllers to memory. So lots of things get connected this way. Okay. This is how your computer system looks like at the hardware level. When we go to the final few chapters of this course, you will learn about a concept called as DMA. It is basically, it stands for direct memory access. Okay. So as I told you, the CPU can access the memory directly. Okay. This connection is always there. That is how code runs. The CPU cannot run anything directly on its own. It needs to refer to memory to say, what do I need to run? Can you give me the code that I need to run? Then that comes from memory. But at the same time, the graphics adapter also needs to know what to show on the screen and where is it going to get that from. Well, then it can do two things. It can either request the CPU that can you read contents from memory and then give it back to me so that I can put it into my internal memory and then show it on the monitor. Well, then the CPU is going to be interrupted from time to time. Give me more, give me more. But the CPU then will not be able to do whatever it is supposed to do. For example, computation. It is going to be interrupted so many times. Give me more data, give me more data. So, it might be spending most of its time fetching data from memory and then just passing it on to the graphics adapter. But what direct memory access helps us do is the graphics adapter can ask permission from the CPU one time saying that, okay, I need control of the memory bus. Okay, then what can happen? The CPU can say, okay, I am doing something important. I do not need access to the memory at this point of time. Then I am giving you access to the memory, direct access to the memory. Do whatever you can after you have copied your data from memory, then send an interrupt to me saying that, you are done copying your data instead of having to fetch the data through me, through the CPU. That's what is direct memory access. And we will look at that in details towards the end of this course. Okay, so then I almost started talking to you about interrupts. So let's get into details about what interrupts are and how they help the system. Okay, so there are two kinds of processes, by the way. So if I say write processes here, a process is basically a live program. So a program which is lying dormant on the disk becomes a process when you double click and start running it. Right? So there can be two kinds of processes, CPU bound and IO bound. Okay, CPU bound processes do a lot of computations and very little input output. Like they do not refer to disks, they do not show much to screen. Maybe at the very end they might show the result. Okay. So most of the time is spent doing mathematics, right? IO bound processes, for example, this could be one of your typical machine learning training programs, right? So you read from the disk your training set, then you run your decision tree logic on it, right? That is mostly computation from that point. Once the decision tree is trained, then you might want to display the tree to the monitor, saying that, okay, this is how the tree is going to look like. But IO bound processes, for example, so they refer to disks and the screen, or they wait for input from the keyboard, right? So they do very little computation. An example might be a file copy program. I mean, very little computation is involved. All it does is that takes a file from the source and puts it in the destination. So basically this involves disk access and this also involves disk access, right? So this is basically an example of an IO bound process. Very little CPU intervention is required. Okay, so now let's see how the CPU can then give its attention to both of these kinds of processes while trying to remain busy most of the time, right? So we don't want an idle CPU, right? It should be working or doing something most of the time. So the CPU usually runs CPU bound processes most of the time. Okay, so at one point of time, maybe it runs one input output bound processes, right? After running that for a little bit, it is very clear that the process will tend to ask for some kind of input output. It might say, I need contents of this source file so that I can copy it to the destination, right? The CPU is then going to say, well, there is nothing for me to do here. Then the operating system is going to put this IO bound process in the waiting state. Because reading from the disk is going to take time. Okay, this basically takes time, way more time than your CPU should be waiting. It can then resume working on a CPU bound program in the meantime, right? Why waste time? So this input output bound process is then put in the waiting state. and the operating system then triggers a read from the disk. Okay, so that is going to take its own time. So when the read from the disk is over, the disk controller, okay, so basically there is a disk controller, as we saw in the previous slide. This is connected to the disk. So once the disk is done reading its file, it will then transfer the data to the buffer present in the disk controller. The disk controller is then going to raise an interrupt. Okay, as the word interrupt suggests, it is going to interrupt the CPU and tell it, stop doing whatever you are doing, pay attention to me. Okay, so the CPU is going to be interrupted. The CPU is doing what right now? It is probably executing some CPU bound process, but it will be interrupted. The CPU is then going to look at the kind of interrupt, and then it is going to handle the interrupt. Okay, so we will see in the next slide how that happens, but in brief, it handles the interrupt, it copies the data from the disk controller, okay, and then the operating system is then going to wake up this process. So this process, instead of waiting, will now be ready. Whenever its time comes, it is then going to be put on the CPU. Since it is input-output bound, very soon it will say, put the contents of this file into the destination location. Then again, a write request to disk will happen. This process is then going to the waiting state. The CPU will continue executing another CPU-bound process until the disk write has been done. When the disk write has been done, then the disk controller is again going to raise an interrupt saying that, hey CPU, listen to me, stop doing whatever you are doing. The CPU says, okay, what's the case here? Okay, file copy, a file has been written. Okay, the operating system is then going to change the status of this waiting input-output process to ready, and then its job will be done. Okay, is this making a little bit of sense to you?
Yes, sir. So
Okay.
means the purpose of disk controller is to interrupt the CPU when the purpose is done.
Yes, that is one of its jobs, right? Its other jobs is also to kind of manage multiple disks connected to it, right? When the OS says, okay, go to this disk and then write this amount of data, then that is all that it tells the disk controller. But giving low-level commands to the disks so that the disks understand what is supposed to be done is the job of the disk controller. The computers are always, built on levels of abstractions. So it is not the job of the OS to issue specific commands for specific disks. It will say something that looks very abstract, and then it's a job of the disk controller to then figure it out how to talk to the disks, right? So that's the job of the disk controller. We will look at it in further details when the chapter on input-output comes towards the end of the course. Okay. So as I was telling you, when an interrupt is raised, the CPU stops doing whatever it stops doing, right? So the CPU, so let's look at the timeline of a CPU. So the time is flowing in this direction. So the CPU is executing a CPU bound task. And then an interrupt comes. So the CPU, what is it going to run now? Well, it is going to figure out what kind of interrupt it is. Okay, basically we assign numbers to different interrupts. Okay, so let's just say this is interrupt number 2. That is some kind of interrupt. Maybe the disk interrupts have their own numbers. The interrupts coming from the keyboard has its own number. So different sources of interrupts have different numbers. So once the CPU figures out the source of the interrupt, then there is something called as an interrupt vector table. Okay, IVT. So here, for example, 0, 1, 2, all the way up to n-1. So here you will have different addresses. So the CPU will then say, okay, this is interrupt number 2, and this is the address that I need to go to. So it is going to jump to that address. Okay, whatever address it finds here, it is going to jump to that address. So that address is usually located in operating system code. Okay, so this jump will happen to OS code. Okay, this is where the interrupt handler is going to be there. Okay, the interrupt handler for number 2 maybe. So this is part of the operating system code, right? So then this handler is what the CPU is going to run here. Okay, so it runs the handler. Once the operating system is done handling the interrupt, which for this example, data is there in the buffer of the disk controller, copy that data to memory. Okay, so that it is available for the waiting process. Okay, the waiting process wanted to read something from disk. Well, we need to bring it to memory, to RAM, right? So the interrupt handler is going to do that. Read it from the buffer of the disk controller, bring it to memory. Once it is there in memory, it can tell the CPU, now you continue doing whatever you are doing. So the CPU will then say, okay, I will continue with the previous thing that I was doing, which is go back to the CPU bound process. Again, an interrupt might come, and then it will figure out the number. Okay, this is interrupt number n-1. It goes there, figures out the address, where to jump. It then jumps to OS code, okay, where the interrupt handler for interrupt n-1 is present. That is going to be put onto the CPU, right? It will execute that. Once it is done, then it will again go back to running the CPU bound thing. This is how the interrupt mechanism works. You interrupt the CPU, it takes care of that interrupt, then it goes back to doing whatever it is doing. Is that idea making a little bit of sense to you, guys?
Yes, sir.
All of these things will become way more clearer as we progress through the course. Okay, just kind of let these things land on your ears for now, and then this will all make a lot of sense later. Okay, but the sources of interrupts are not always hardware interrupts. So hardware interrupts can be, coming from keyboards or your disk controllers or your mouse. Every time you move the mouse, you're making thousands of interrupts. So you might ask, Jyoti, if the CPU gets thousands of interrupts every second, then what does it do then? Does it always cater to interrupts? No, the CPU is very, very fast. It runs at speeds of like billions of cycles per second. Like a 5 gigahertz CPU is running at 5 billion cycles per second. So a number of 1,000 is not a big number in front of that, right? For you, it might be very big, because if we get interrupted, twice in 1 hour, then we might become very irritated. Like, stop interrupting me, I'm doing what I'm doing. But for the CPU, 1,000 interrupts per second is a very low number, because that's for the fact the CPUs are very, very fast. So keyboards, disk controllers, your mice, all of these things can issue hardware interrupts for the CPU to pay attention to. But even software can also raise interrupts. For example, if you divide by 0, what happens? Your program doesn't know what it is doing, so the operating system will be alerted by the processor. So when you divide by 0, the processor itself, the CPU itself, is going to generate an interrupt for itself internally. Okay, maybe it is interrupt number 5. Then it will go to this table here, this interrupt vector table. It will look at number 5. It will figure out the code. It will jump to the OS code and ask the OS, how do you want to handle a divide by 0 case? Interrupt handler 5. And the OS tells, okay, the OS will want to figure out which process was running on the CPU at that point of time. Okay, the OS is very angry, just like an angry parent. Oh, how dare you divide by 0? I am going to kill you. Well, parents don't do that. The OS does that. Right? The OS is going to kill that process because it is considered unsafe at that point of time. Okay, and then it is going to go back to doing whatever it is doing. So software can also raise interrupts. Hardware can also raise interrupts. Okay. Another thing is that, I was talking to you about system calls, right? So even system calls, so let me use the space over here to kind of tell you how a system call works in more amount of detail, right? So that, these things are clear to you. These are very important things to be kind of, a little bit clear to you when we proceed any further. Okay. So let's just say you write a program and you say, and then you say int and then you say, I want to do a printf. Okay, and then that's all you want to do. And you try to run this program. So when this line is going to be executed, what do you expect this to do? You expect hello to be printed on the monitor, right? But then you might have guessed that you need the help of the operating system. Without an OS, this code is not going to work because you cannot get direct access to the monitor. It is not allowed. You have to go through the OS, right? Each program that you write has 3 special files given to it, okay? And those files are basically standard in, standard out, standard error. The operating system usually connects standard in to the keyboard, standard out to the display, and standard error to the display, okay? But your program need not worry about where it is connected to. What printf does is it takes a string and then sends it out on the standard out file. This is a file. This is connected to a display. Printf is not worried about that. As you will see in the lab, that we can connect standard out to many different things. We can make it connected to a display, you can make it connected to a printer, or you can make it connected to another file itself, like a regular file. So whatever you put in printf, it actually is going to another file like out.txt. Okay, so standard out might be connected to any of these devices, but for printf, it is standard out. It does not care where the OS has connected it to. So printf then issues a system call saying that write to standard out this string. Okay, this is basically a system call. So the system call is going to be made into the operating system. Okay, but look at the CPU. What is the CPU running right now? And here is the time axis, right? The CPU is running your program. And then at one point in your program, it will try to run the write system call. I mean, the write system call is there inside the printf, the code for printf. You don't write that code because you call the printf function. Well, the function itself will have its code, right? So that in turn calls the write system call. At one point, you will call the write system call. And your CPU is going to execute this. Okay, the CPU is now executing this. Well, how is it then going to invoke the OS? What methods do we have to call code into the OS? One way is interrupts. As you saw, the CPU was executing a CPU bound process in the last slide, and then when the disk was done reading data, it raised an interrupt. What did that do? It stopped the CPU from doing what it was doing. It went to the interrupt vector table, figured out the number of the interrupt, and then called the interrupt handler, the thing that will handle the interrupt. And that was operating system code. It is the operating system which basically provides those handlers, right? This is also going to do the same thing. This is going to raise a software interrupt or a trap. Software interrupts are also called as traps or exceptions. Okay, a trap will be raised. What will happen? The CPU will stop doing what it is doing. Okay, so let's just say the system call interrupt number is like 50. Okay, so the CPU is going to go to the interrupt vector table, go to item number 50, figure out the address, and then jump to OS code and go to the handler, interrupt handler for number 50. This is basically maybe the system call handler. The system call handler will then figure out, okay, which system call was that? Okay, write system call. Okay, where do you want to write to? Okay, standard out. What do you want to write? Hello. Then it will figure out the rest of things, whether you can write or not write, but it will, authorize the request, right? Whether you're allowed to write to that thing or not. And then at some point, it is going to talk to the device driver for the monitor and then it is going to print hello, put a new line, and then it is going to resume the processor, saying that, okay, now you can go back and run whatever you are running. So the processor will come back to your program again. Okay, and then it will exit from there. Okay, this is how kind of system calls work. System calls are nothing but exceptions or interrupts. Okay, and this is interrupts are kind of the only way in which you can switch from user programs, your programs, to operating system code, and then come back from operating system code back to your program. Okay, there is no other way. Basically, your processor is running something, you need to interrupt the processor, like, okay, now you need to do something else. Okay, is this making a little bit of sense to you?
Yes, sir.
Okay. There is another mechanism, and we will do these things multiple times. Don't get overwhelmed that, okay, this is the only time Jyoti is going to talk about this, and then this is very confusing. This is confusing for me also. So when I started learning this, it took me many years to understand all of this. So don't worry, we will do these things in like 10 more times in the class. Okay, just come to the classes and pay attention, and we will have doubt solving classes. So don't get overwhelmed by what is happening here. Okay. So interrupts are one way to handle input output and system calls. Well, there is another way of doing input output. It is called as polling. In polling, basically what we do is, right, so the CPU tells the disk controller that, okay, write this data to disk, and this is going to take, let's just say, 5 seconds. The CPU will not be executing anything else in the meantime. It will keep asking the disk controller, are you done? No, not done. Are you done again? Not done. It will do this. It will keep polling, bugging the disk controller. Are you done? Are you done? Are you done? At one point, the disk controller is going to say, okay, I'm done. Then the CPU will then move forward to do something else. This is called as polling. This is complete opposite of what interrupts are. In interrupts, the CPU says that, okay, I've given this task to the disk controller. I'll continue doing something else. You come back and interrupt me whenever you are done, and that's when I'm going to pay attention to you. Polling is completely different. It's like the CPU does nothing else, keeps asking, are you done? Are you done? Are you done? Do you have data for me? Do you have data for me? Right? Until it satisfies what the CPU wants. So the CPU is basically wasting time and doing nothing. Okay, so no one uses polling. Interrupts are basically the standard way of dealing with input output and system calls. Is my screen still visible or not?
Not sir.
Okay, it stopped.
It stopped? Okay. It's just locked my screen, so that's why it stopped. I'm gonna share the screen again. It's visible now?
Yes, sir.
Okay, so I was showing you the interrupt timeline, right? So as you can see here, the CPU and the time is flowing in this axis right now. The CPU is executing a user process. Okay, it's executing the user process. Oh my God. And then the input output device is idle in the beginning, but then it starts to do some transfer. When the transfer is done, it raises an interrupt to the CPU. The CPU will then stop doing whatever it was doing. It will handle the interrupt here in this region. As you can see, this is for IO interrupt processing. The interrupt handler is running at this point. The CPU has stopped executing the user process. Once it has taken care of that, then it will go back to running your user process again. Then at some point of time, someone will request an IO request, and the input output device will then continue working on that, the transferring mode. Once it is done, it is going to interrupt the CPU. The CPU will then start executing the interrupt handler at that point of time. When it is done, it is going to go back and execute the user process again. Okay, so the CPU keeps doing its normal thing. It listens to interrupts from time to time, takes care of whatever the interrupt is about, goes back to doing whatever it was doing in the first place. So this is basically what we have been talking about in all these slides, right? So when the input output starts, the control returns to the user program. Okay, only upon input output instruction. So wait instruction idles the CPU until the next interrupt. So this is basically, what polling does, kind of like this is not how interrupts work. But interrupts are, how this thing is about. So after input starts, control returns to the user program without waiting for input output completion. Okay, so just keep in mind these two things. In polling, you basically kind of get into a wait loop and then keep waiting for that thing to work out, and then you continue further. And interrupts, you continue to do whatever you are doing. When the interrupt comes back to you and you say, okay, you are done with the transfer, or there is something on the keyboard waiting for me, or the mouse has moved, or whatever, I need to take care of that. And then it'll take care of that interrupt depending on how the interrupt handler is written. So this is the stuff that you already know. A byte is made up of 8 bits. Kind of know that. A kilo is basically, always keep in mind, these are all powers of 10. So a kilobyte is basically 2 to the power 10, megabyte is 2 to the power 20, gigabyte is 2 to the power 30, terabyte is 40, and petabyte is 50. Always keep this in mind. Okay, they're not powers of 10. They're powers of 2 as far as OS and architecture is concerned. Anyway, so we will continue with the rest of it in the next class, and very soon we'll be done with introduction, but this is very, very important to give you an overview of how the system is structured and what different subsystems are, what different subsystems do in the OS. And then we will look at all of those subsystems like processes, memory management, disk management, synchronization, deadlocks, and all of these things in details through the rest of the course. Any questions for me at this point of time?